Binomial radical expressions. Algebra 2, Lesson 6-3. I would like to just warn you that this is a really good section to do some Cornell notes, and there's going to be quite a few for this one. So at this point, I would get out a piece or two of paper and get your Cornell notes set up. Our objective in this lesson is for the student to be able to identify like radicals. You're going to be using addition, division, multiply, and subtraction to simplify them. And we're also going to be talking about conjugates and how to rationalize binomial denominators. So hopefully you notice there's a couple things that are underlined. These are our terms like radicals, conjugates, and rationalize. We've talked about the rationalize before, but we are going to talk about it in terms of binomial denominators, and that's one that you should know as well. Okay. So far with radical expressions and simplifying, we have learned that we can multiply and divide them as long as they have the same root. And here's some examples. We're multiplying. If I can multiply what's in my roots as long as it's the same root. This one is the square root, and that helps us simplify. Or I can divide, and once again they have to have the same root. So this is something to keep in mind, and that helps me simplify. Well, this particular lesson shows us that we can also combine like radicals. There's our first term that we need to remember to learn. And this is the adding and subtracting part. So we've learned how to multiply, divide. Now we're going to use adding and subtracting. Like radicals can be combined, and we call it combining them rather than so much adding and subtracting. And we can only combine them when you have the same base and the same root. We have 5, the cube root of 5 in both places. So in this case, if I take the 8 cube roots of 5 plus 3 cube roots of 5, I end up with 8 plus 3 is 11. 11 cube roots and 5. This is kind of like having when we had 11x, or 8, if we call this 8x plus 3x equals 11x, where our x is just the cube root of 5. So, this is not exactly adding though, and I want to point that out because I don't want you to think you can just do any kind of adding with it. For example, and I want to show you that this does not work. If I take the square root of 2 plus the square root of 3, and I'm thinking, well, if I add those, it should be the square root of 5. Well, it doesn't exactly work that way. See, if I would put on a calculator the square root of 2, I would get something like this, 1.414. And the square root of 3 is something like 1.732. And remember, these are both irrational numbers, so of course, this is not the end of the number, this is just the first 3. And if I add them together, I get 6, 4, 11, carry the 1, 3. So the square root of 2 plus the square root of 3 equals something on the order of 3 and 146 thousandths. However, if I put the square root of 5 into my calculator, I get 2 and 236 thousandths. So they are not equal. So you're not adding. And definitely this also shows us that you cannot add unlike radicals. Okay. However, so let's do some examples. This is what your problems will say. Combine if possible. So we look at the first one. And I get a piece of paper and do one at a time. That one's not a very good one. Just look at the first one. We have 3 times the square root of 5x minus 2 times the square root of 5x. Are these like radicals? Well, we have both the square roots, and they're both to 5x, so yes, so I can combine. Then I take 3 minus 2, and I get 1 times the square root of 5x, or I don't need to put the 1 there, I can just say the square root of 5x. But let's look at this one. I have 6x squared times the square root of 7 minus 4x times the square root of 5. This is not like in more than one way. Not only do I not have the same root underneath, but I also have different variables at different, well, the same variable, but at different powers. So this one is what I would call already simplified. Your book probably says not possible. I'm going to just put that. Okay. So that one I can't do anything with, so basically. So let's look at the third one. 3x times the square root of xy plus 4x times the square root of xy. This time I have the same variable at the same power, the same root, square root, and the same base in my square root, xy. So these I can add together, and I would just combine their coefficients. 3 plus 4 is 7x square root of xy. All right, now let's look at the last one. The square root of 12 plus the square root of 75 minus the square root of 3. Well, I hope you can tell that these are not the same roots, so it doesn't look like it can be simplified. However, I want to bring in our little list from the last time about simplified radical expressions. First is that they contain no math operations that can be done. And as you saw before, we couldn't add or subtract it the way they were. But number 2 says they contain no radicand with a perfect nth, in this case, square factor other than 1. Well, let's look back at that again. The square root of 12 plus the square root of 75 minus the square root of 3. Now I know that some of you are having a little bit of a difficulty figuring out what the square root factors are, so I thought I would show you another way to look at this. We can kind of do a factor tree under our bases here. 12 can be broken into 3 times 4, and 4 can be broken into 2 times 2. This is a square root, which means there's kind of a invisible 2 up here, which means I have to have a pair of roots to be able to get out of here. So in this case, the square root of 12, this 2 can be pulled out of my square root, because there's 2 of them, and I'm left with, because if I take those away, I'm left with 3. So 12 can also be written as 2 times the square root of 3. That's not a very pretty square root symbol. Okay, go on. Similarly, I can factor 75 as 3 times 75, or 25, I'm sorry, 3 times 25, and 25 is 5 times 5. So once again, I have a pair, or 2 numbers, so if I have 2 numbers, I can take them out. Those 2 numbers become out 5, and I'm left with my 3 inside. And then I have just the square root of 3. Now, all of a sudden, I have the same root of the same base, the square root of 3, on all of these. And I can combine them. So sometimes, even though I start out with something that doesn't look like it can be combined, once I simplify it, then I can do the combining. So in this case, I have 2 square roots of 3 plus 5 square roots of 3, that would be 7, minus, and there's that imaginary 1 here, 1 square root of 3, so I end up with 6 square roots of 3. 6 times the square root of 3, and that's my answer. Let's look at another one like that, just to make sure we've got the hang of it. We have the cube root this time of 250 plus the cube root of 54 minus the cube root of 16. Now the thing that's telling me that I need to probably do something here is that these are all cube roots. So that kind of gives me a little bit of a hint that maybe I should try simplifying first. So I'm going to do that. And I'm going to try it the same way I did last time with the factor trees. Although if you see the cube root here and you know what it is, you can do it that way as well. Either way works. So if I look at 250, well, that's 25 times 10, right? And 25 times 10 can be, 25 breaks down to 5 times 5. And 10 breaks down to 5 times 2. And since I have a 3 up here this time, I need sets of 3 to get out of here. So I have 3 5s right here. So that means I can pull 5 out. 5 gets out of the, if you call this the little box or the jail. So 5 gets out of jail, but 2 stays in. So it's 5 cube root of 2. How about this one? Well, I can break down 54 as 9 times 6, right? 9 is 3 times 3, 6 is 3 times 2, and once again I have 3 3s. The 3 gets out of jail, or the box, and I'm still left with the cube root of 2. Looking promising here. Okay, so the last one, 16. 16 is, well, let's see, 4 times 2. 4 times 4, I'm sorry. 4 times 4 and 4 times 4. Both of those can be broken down to 2 times 2. Well, I have 3 2s. Those can come out, and even though I have, the fourth one is still a 2, it has to hang back. It needs 2 more buddies to get out. So we can take the 2 out. So it's minus 2 times the cube root of 3. And look, once again, I have like radicals. All of them are cube roots of 2, or cube roots of 2, yes. Okay, so we have 5 plus 3, which is 8, and 8 minus 2 is 6. 6 cube roots of 2. Okay, so hopefully that makes that a little bit more clear. So remembering that sometimes you can simplify the roots to get them so that they can be combined is a really important thing. Well, that brings us to another thing that we might be able to do. Now that we're able to do the adding and subtracting, we can multiply binomials that have radicals in them. Remember, a binomial is an expression of 2 monomials. So in other words, in this case, one binomial is 4 plus 2 to the square root of 2, or 2 times the square root of 2. And the other binomial is 5 plus 4 times the square root of 2. And this should look like something you've done before, except usually you've had x's or y's or some other variable here. Well, it doesn't really matter. We can still use the same process that you have in the past, which is the FOIL method. And we do it the same way. I want to remind you, FOIL stands for first, outer, inner, last. FOIL. So we're going to do the first one. So we'll take the 4 times the 5. I'm going to write it out. Now you